So today we're going to be solving problems from chapter 6 of the textbook. Okay, so let's start working on the first problem. This is going to be problem 1.6 from the textbook, and basically we want to consider this chemical reaction forming zirconia, beta zirconia at 1600 K, and we want to calculate the change in enthalpy and entropy for this reaction to occur. So this is going to be a fairly straightforward calculation, although a little bit lengthy. And there's just a few tricks along the way. So let's start out with the enthalpy. So delta H 1600 is equal to the enthalpy of the products beta at 1600 minus the enthalpy of the reagents. Plus HO2 1600. Okay, let's do the product first. And when you look in your textbook, something that you should notice is that for ZrO2, they give both an alpha and a beta phase. This is the heat capacities, and then they give the temperature range over which they're valid. So alpha is valid from 298 to 1478, and beta from 1478 to close to 3000, the melting temperature. Also, if we look at the table on the molar heats of transformation, for ZrO2, there's a transformation from alpha to beta at 1478 that's given. So that means that we actually have to take our reaction and put it through a phase transformation. So HZrO2 beta 1600 is equal to delta H, a formation of ZrO2, and this is going to be alpha phase, because alpha phase is the low temperature phase, plus the integral from 298 to the transformation temperature, which is 1478, the heat capacity of ZrO2 alpha dt plus delta H, a transformation going from alpha to beta, plus the integral from the transformation temperature 1478 1600 of the isobaric heat capacity ZrO2 beta dt. Okay, so from the table in your book, we have the heat of formation at 298 for alpha ZrO2, and that is minus 1.1 times 10 to the 6 joule per mole. And from the table on enthalpies of transformation, we have the latent heat going from alpha to beta as 5.9 times 10 to the 3 joule per mole. So now we just need to figure out these two integrals. This first integral is the integral from 298 to 1478 of the heat capacity, which, looking this up from the table in the book, is 69.62 plus 7.53 times 10 to the minus 3 T minus 14.06 times 10 to the positive 5 raised to the t to the minus 2 dt. And integrating this, we get 8.63 times 10 to the 4 joule per mole. So that's going to go into there. And the second integral is the integral from 1478 to 1600, and the heat capacity is 74.48 dt, which gives us 9.09 times 10 to the 3 joule per mole, which goes into that integral, which means that HZrO2 beta at 1600 is minus 1.1 times 10 to the 6 plus 8.63 times 10 to the 4 plus 5.9 times 10 to the 3 plus 9.09 times 10 to the 3, or HZrO2 beta 1600 is equal to negative 9.99 times 10 to the 5 joule per mole. I'm going to do this out to 3 sig figs. Okay. So now we have to do the enthalpy of zirconium and oxygen. And looking in your textbook again, we have another transformation. In this case, zirconium transforms from the low temperature alpha phase to the beta phase at 1136. So, writing out our enthalpy we get HZR1600 is equal to delta H formation ZR alpha at 298 plus the integral from 298 to 1136, the transformation temperature, times the heat capacity of the alpha phase, dt, plus delta H of transformation, alpha to beta, plus the integral from 1136 to 1600 K Cp of the beta phase dt. Okay, zirconium is an element, and at standard temperature and pressure, the alpha phase is the ground state, or the naturally occurring state. So we've defined that to be 0. The textbook gives us the enthalpy of transformation. That's 3.90 times 10 to the 3 joule per mole. As first integral is the integral from 298 to 1136, and the heat capacity of the alpha phase is 22.84 plus 8.95 times 10 to the minus 3 T minus 0.67 times 10 to the 5 T to the minus 2 dt, which is equal to 2.44 times 10 to the 4 joule per mole. And then the second integral is the integral from 1136 to 1600 of 21.51 plus 6.57 times 10 to the minus 3 T minus, plus 36.69 times 10 to the 5 T to the minus 2 dt. And integrating this, we get 1.51 times 10 to the 4 joule per mole. So HZR 1600 is equal to 2.44 times 10 to the 4 plus 3.9 times 10 to the 3 plus 1.51 times 10 to the 0 times 10 to the 4 HZR 1600 is equal to 4.34 times 10 to the 4 joule per mole. Okay, now we need to do oxygen. Oxygen, there's no phase transition, so this one has considerably fewer steps. HO2 at at 1600 is equal to delta H of formation of O2 at 298 plus the integral from 298 to 1600 Cp of O2 dt. Again, oxygen is elemental, and at 298 it's in gas phase, so this we defined as 0 joule per mole. Then the integral becomes the integral becomes 29.96 plus 4.18 times 10 to the minus 3 t minus 1.67 times 10 to the 5 t to the minus 2 dt is equal to 4.37 times 10 to the 4 joule per mole. So HO2 at 1600 is equal to 4.37 times 10 to the 4 joule per mole. Which means that we can now write delta H at 1600, or let's, delta H at 1600 is equal to H ZrO2 beta 1600 minus H Zr 1600 plus H O2 1600 is equal to negative 9.99 times 10 to the 5 minus 4.34 times 10 to the 4 plus 4.37 times 10 to the 4 delta H 1600 is equal to minus 1.09 times 10 to the 6 joule per mole. Okay, that's half of our problem. Now we need to look at the entropy. So the entropy, delta S, 1600, page 3, page 3 or page 4? It's page 4. Is equal to S Zr O2 beta, that's 1600, minus S Zr 1600 plus SO2 1600. Okay, doing the products first, or the product. S ZrO2 beta 1600 is equal to delta S, the formation of ZrO2 alpha phase at 298 plus the integral from 298 to 1478 isobaric heat capacity of the alpha phase divided by T dt plus now we need the change in entropy that occurs for the transformation, and the change of entropy is going to be given by delta H alpha to beta divided by the temperature of transformation, which is 1478 plus the integral from 1478 to 1600 Cp of the beta phase over T dt. Okay, we can find this, and that is 5.04 times 10 to the 1 joule per K mole. This is 5,900 divided by 1478, which is equal to 3.99 joule per mole K. The first integral is the integral of 298 to 1478 of T to the minus 1 times 69.62 plus 7.53 times 10 to the minus 3 T minus 14.06 times 10 to the plus 5 T to the minus 2 dt, or 1.13 times 10 to the 2 joule per mole K. And then the second integral is the integral from 1478 to 1600 T to the minus 1 times 74.48 dt is equal to 5.91 joule per mole K. Okay, that means that for our product SZrO2 beta at 1600 is equal to 5.04 times 10 to the 1 plus 1.13 times 10 to the 2 plus 3.99, or SZrO2 beta at 1600 is equal to 1.73 times 10 to the 2 joule per mole K. Okay. Now going to the reagents. Let's do the easy one first. We'll do oxygen. S of O2 at 1600 is equal to delta S of formation of O2 at 298 plus integral from 298 to 1600 T to the minus 1 Cp O2 dt. From the table in the book, this is 2.05 times 10 to the 2 joule per mole K. And the integral is the integral from 298 to 1600 t to the minus 1 times 29.96 plus 4.18 times 10 to the minus 3 t minus 1.67 times 10 to the 5 t to the minus 2 dt is equal to 5.49 times 10 to the 1 joule per mole K, which gives us the net SO2 1600 is equal to 2.05 times 10 to the 2 plus 5.49 times 10 to the 1. SO2 is 1600 is equal to 2.60 times 10 to the 2 joule per mole K. Okay. And now, last step is to get zirconium. So, S of ZR 1600 is equal to delta S, the formation of ZR alpha phase at 298 plus the integral 298 to transformation temperature 1136 of Cp alpha phase over T dt plus delta H alpha to beta divided by 1136. So that's the change in entropy with transformation from alpha to beta, plus the integral, this is page 5, of Cp beta over T dt from 1136 to 1600. Okay. This we find to be 3.90 times 10 to the 1 joule per mole K. That is 3900 divided by 1136, which is equal to 3.43 joule per mole K. The first integral is the integral 298 to 1136 t to the minus 1 of 22.84 plus 8.95 times 10 to the minus 3 t minus 0.67 times 10 to the 5 t to the minus 2 dt. Completing the integral, we get 37.713. That's joule per mole K. Now the second integral, that is the integral from 1136 to 1600 t to the minus 1, 21.51 plus 6.57 times 10 to the minus 3 t plus 36.69 times 10 to the plus 5 t to the minus 2 dt. And completing that integral, we get 11.120 joule per mole K. Which means S of Zr zirconium at 1600 is equal to 3.90 times 10 to the 1 plus 3.77 times 10 to the 1 plus 3.43 plus 1.11 times 10 to the 1. SZR 1600 is equal to 9.12 times 10 to the 1 joule per mole K. Okay, almost there. Now we're going to put this all together to get delta S 1600 is equal to S ZrO2 beta 1600 minus the entropy of zirconium 1600 plus the entropy of oxygen gas at 1600, which is 1.73 times 10 to the 2 minus 9.12 times 10 to the 1 plus 2.60 times 10 to the 2, or delta S at 1600 is equal to 1.78 times 10 to the 2 joule per mole K. And that is solving problem 6.1. To say, it's steps you really through how to think about the basic steps. Not a particularly riveting problem to work on, but it is a pretty good example of how to work with these types of concepts. Okay, now let's look at problem 6.4 from the textbook. So the wording in this problem is a little bit tricky. Basically, we're saying that if we have copper at 298 K and 1 atmosphere, if we raise the pressure at constant temperature from 1 to 1000 ATM, how much does the enthalpy change? And given that, how much does the temperature have to raise if we were to increase the temperature at constant pressure to yield the same change in enthalpy? Another point to note here is that I'm using my old version of the textbook from when I was an undergrad, and there's a typo. So those of you that have the 5th edition, you'll have this correct. Those of you that have the 3rd and the 4th edition, this should be 10 to the minus 4. Because that's the, this is a relatively large. It's a huge coefficient of thermal expansion. So, okay, so let's write this out. So basically, we're going to say that the change in enthalpy due to change in temperature star Cp dt delta H const pressure is equal to the change in enthalpy at constant temperature, which is going to be this: P1 to P2 V1 minus alpha T dP is equal to delta H constant temperature. Okay, so let's get this first. So that's the integral from 1 to 1,000 atmospheres times V, which is given as, where's that at? Here it is, 7.09 cubic centimeter, and we're going to be working in liters, so that is 7.09 divided by 1,000. So that is the in liters times 1 minus alpha, which is 0.493 times 10 to the minus 4 times temperature, which is 298, and then all of this is giving us liter atmosphere, and because we're working in joule per mole, then this has to be times 101. That's joule per liter atmosphere. And if you do this, this yields, what comes out of this? What comes out of this is 7.05 times 10 to the 2 joule per mole. Okay. So then, going back and setting these equal, we get 705 is equal to the integral from 298 to T star, and then the heat capacity of copper is 30.29 minus 10.71 times 10 to the minus 3 T minus 3.22 times 10 to the 5 T to the minus 2 dt. And when you solve this, you're going to find 3 roots. You're going to find T star is equal to 34.6, 328, and 5,290. Well, we know that we have to put energy into the system, so it can't be decreasing the temperature. This is above the melting temperature, therefore that's the answer. So we have to heat from 298 to 328 K to get the equivalent change in enthalpy with to having the pressure change from 0 to 1000. Okay, so now let's work on problem 6.6, which I think is a challenging problem. And what I found challenging about it was that solving this problem really relies on one key observation, and that is recognizing that we're working with an adiabatic vessel. So with this adiabatic vessel, it means that we have no heat coming in or out of the system, which means that the final and the initial enthalpy of the system is going to be the same. Also, let's mark here that this is 973 K. So the trick here then is to determine the two enthalpies and take the difference, and that will let us solve for this. So the basic premise of the problem is that we've got some amount of molten aluminum, liquid aluminum, and we throw into it Cr2O3. The Cr2O3 is reduced to chromium metal. The aluminum is oxidized, and then there's going to be some excess Cr2O3 that's thrown in addition to the initial load, and that's going to be left over. The reaction is 2Al liquid plus Cr2O3 solid goes to Al2O3 solid plus 2Cr solid, and then plus excess reagent. We have 1,000 grams of liquid aluminum. So that means we have 1,000 grams times 1 mole of aluminum per 26.98 grams, which means the NaL, the number of moles of aluminum, is equal to 37.06. And we'll be using that. Unlike other problems where we do all of our work in molar quantities, in this system we're going to be working with absolute values of the enthalpy because we're interested in knowing the total heat that's generated during the reaction. So let's start by writing out the initial enthalpy. So the initial enthalpy of the system is going to be, starting out with the molten aluminum, n moles of aluminum, and delta H formation of aluminum solid, which is 0, plus the integral 298 up to the melting point. And aluminum melts at 934 K, and you can see that from the table in the back of your book. So 298 to 934 K, heat capacity of Al solid dt plus delta H of solid to liquid plus, and the rest of the path, that's from 934 to 973, heat capacity of liquid aluminum dt. So that's the first bit, and the next part is we're throwing in the chromia plus NCr2O3 times delta HF Cr2O3 at 298 plus the integral from 298 to 973 Cp Cr2O3 dt. Okay. So this then is equal to 37.06 times the integral 298 to 934 of 31.38 minus 16.4 times 10 to the minus 3t minus 3.6 times 10 to the 5 t to the minus 2 dt plus the enthalpy of transformation, which is 1.07 times 10 to the 4 plus the rest of the integral here on the right, integral from 934, 973, and this is 31.76 dt. Plus the chromia contribution, that's NCr2O3 times the quantity minus 1.13 times 10 to the 6th. That's the enthalpy of formation of solid chromia, plus the integral 293 to 973 of 119.37 plus 9.3 times 10 to the minus 3t minus 15.65 times 10 to the 5 t to the minus 2 dt. Evaluating this, we get H initial is equal to 9.13 times 10 to the 5 minus 1.05 times 10 to the 6th times NCr2O3. And at the end of the day, that is what we're looking for. Okay, so now let's get the final, the enthalpy. So the final enthalpy is equal to, so let's do the Al2O3 first, and for every 2 mole of aluminum we have 1 of Al2O3, so we have NaL over 2, half as many moles of Al2O3, times delta H formation, Al2O3 at 298, plus the integral from 298 to 1600 of the heat capacity of Al2O3 dt. Now let's get the chromium contribution. So that's plus NaL. So for every 1 mole of aluminum, we have 1 mole of chromium. We have NaL. Times the enthalpy of formation of chromium at 298, which is again 0, plus the integral from 298 to 1600 Cp of Cr dt. And then let's put in the chromia contribution, and this is the residual excess chromia. So the residual excess chromia is going to be NCr2O3. That's what we're putting in, but then some of it disappears because it reacts. And it reacts for every 1 mole, or for every 2 mole of aluminum, we lose 1 mole of chromia, which means that's going to be minus NaL over 2 times the enthalpy of formation of chromia plus the integral from 298 to 1600 CpCr2O3 dt. Okay. Substituting in numbers, we get H final is equal to 37.06 divided by 2 times negative 1.68 times 10 to the 6 plus the integral 298 to 1600, 117.49 plus 10.38 times 10 to the minus 3 t minus 37.11 times 10 to the 5 t to the minus 2 dt. Plus the aluminum, 37.06 times the integral 298 to 1600 sorry, is not aluminum, this is chromium. 21.76 plus 8.98 times 10 to the minus 3 t minus 0.96 times 10 to the 5 t to the minus 2 dt. And now the chromia plus NCr2O3 minus 37.06 divided by 2 times minus 1.13 times 10 to the 6 plus integral 298 through 1600, 119.37 plus 9.3 times 10 to the minus 3t minus 15.65 times 10 to the 5th t to the minus 2 dt. Okay, so we got all that. Let's simplify the integrals now, and that gives us h final is equal to negative 8.87 times 10 to the 6 minus 9.67 times 10 to the 5th times NCr2O3. And now we can solve this by setting h final equals h initial, and that gives us NCr2O3 is equal to 1.20 times 10 to the 2 mole and 1.20 times 10 to the 2 mole times 151.99 gram per mole gives us 18.2 kilograms. 203 of chromia. And that was problem 6.6.